Yes. Lavenderish purple. So I was comparing with Carl, who teaches this class too, my husband, Dr. Snipes, and he got to the same slide as we did. And because I said, anytime a slide says, don't confuse this, it's time to quit. It was that time anyway.
So do we have a pre-lab for tomorrow?
I think so. Yeah. It's Beer's Law. So I think it is pre-lab. So tomorrow, I was also kind of thinking, and Carl thought this would be a good idea, so we'll just make one group of 3 for lab. Does that sound okay? Good. So, and then, yeah. So tomorrow, and we'll just kind of double check, make sure your drawer's there and all that, and dive right into Beer's Law experiment, pre-lab and all that. Okay. So we talked about this. And I'm with me, but we know electronegativities increase as you go from left to right and as you go bottom up in the same group. And that's why our oxygen is partially negative and our carbon's partially positive. This is what we would say that there is a degree of bond polarity. Okay, if those were the same electronegativities, the bond would be nonpolar, but it is polar. Okay, now, don't confuse bond polarity, which we just talked about, the polarity of a bond, with the polarity of a molecule. Now, I was kind of laughing at myself. Well, if your molecule only has 2 atoms, then the bond polarity is the molecular polarity of the molecule. But it comes into play like if your molecule has 2 atoms arranged a certain way, and we're going to see that spatially it makes a difference, how they're arranged spatially. And remember, to know spatial arrangement of the atoms, you have to know the root structure, where the lone pair electrons are, making the different hybridizations. But what I start saying is if you have 3 or 4 or 5 atoms together, in order to understand the polarity of the molecule, we have to start with the polarity of the individual bonds, and then step back and kind of look at it collectively. That's So the polarity of the molecule is figured out by looking at the individual, but they're different. So like down here, it says, for instance, you can have we can have a molecule that, and there's lots of good examples. We have a molecule when we evaluate, we're like, oh my gosh, that bond is polar, that bond is polar, that bond is polar, that bond is polar. But when we look at the molecule is nonpolar, and I'll show you how the bond polarities kind of get canceled each other out to make the molecule nonpolar. Now, sometimes in Chem 2, so I've been doing this a few years, you wouldn't realize it, but this idea of is a molecule polar or not polar, that's a player in all sorts of in all sorts of things we're going to learn in Chem 2. So you need to know the molecule. Don't mean to scare you, but don't blow us up. Okay, so is a molecule going to be polar? Is there some polarity to that molecule, molecular polarity? Well, in order to understand the polarity of the molecule, I told you just a minute ago, we're going to basically have to understand the polarity of the individual bonds and kind of look at them collectively. We call that kind of assessment the net dipole. Okay? So if I was to ask you what your net worth was, you'd say, well, I need to add up my checking account, and if I have a car, I don't know, you're already how many assets you guys have, but you would add up all your assets. That's your net worth, okay? So a net dipole or net dipole moment looks at, it's a question of polarity of the molecule, looking at the individual polarity of the bonds. So we use this Greek letter mu, right? The same Greek letter we use for micro to talk about net dipole moment. So net dipole moment is like the polarity of the whole molecule. So what this says is if your net dipole moment is anything other than 0, And there's no negative. Is there negative at dipole moment? No, I think they're all positive. If it's not zero, then it's going to be polar. So you have a polar molecule. Okay, and then this next one says, not so surprising, if your net dipole moment is zero, then you are dealing with a non-polar molecule.
Can you say again how do we know that dipole moment?
Yeah, this is one of those things where I'm introducing it now, and then I'm going to talk about how you find it. But what I said just in general terms is that we're going to have to understand the individual bond polarities. And I didn't describe how to do it yet. Okay. So I'm building up to that. Now this is weird. There's no molecule CH, I think. No. There's like C2H2, but there's no CH. What I'm trying to show you there is if you have within a molecule somewhere where a carbon is bonded to a hydrogen. Well, and we did this, I think, the other day. If you look at your Pauling value for hydrogen, it's less, and your Pauling value for carbon is more. And I can tell that. Remember what those little vectors mean? Where it begins, that's positive, and where it ends is negative. So this partially negative, partially positive. All right. So the point here is that's a relatively short little stubby vector versus this one. Again, I know that this is just partially positive, even without looking at Pauling values, and this is partially negative. Now, this is stronger. Oops, sorry. That's stronger. Strong. I'll just put strong. Goodness gracious. Because of the length. And we aren't going to get down into using lengths in our analysis, but just kind of put that in the back of your mind when you're looking at them. The length matters to how much of a difference we have in electronegativities. All right, here we go. Let's consider carbon dioxide. Now, again, this is not the Lewis structure of carbon dioxide. But if we were to take CO2, carbon dioxide, and to understand what sort of orbital hybridization you have around the carbon atom, it must be sp. Why? Because I have no lone pair electrons, and I have two sigma bonds that are reaching out. Actually, also I have two pi bonds, but that doesn't give us the hybridization, nor does that give us molecular shape. So here we go. This is your carbon dioxide. If I were to assess each individual bond, carbon, oxygen, carbon, oxygen, they're both polar because they have different Pauling values. There's definitely a delta chi. But the whole molecule is nonpolar. Let's see what my next slide says. This actually, the net dipole moment is equal to 0 here. Trying to think let me see what my next thing says. The reason it's equal to 0 is this. Oh, yes, okay. It's a tug of war. So let's say the middle of me is my carbon atom, and I'm stuck to an oxygen, and I'm stuck to an oxygen. Okay? So I'm pulled this way, the same amount I'm pulled this way. So guess what? It's a wash. There's actually, the whole molecule itself is nonpolar. Now, if I was lopsided, like instead of, and we're going to look at this as an example, so what if I had a carbon, an oxygen, and a carbon and a hydrogen? Well, I'd have to double check, but I think I'm going to be more lopsided that way. Okay, and then I do have a polarity. I do have a net dipole moment is not 0. So let's look at water. So CO2, nonpolar. H2O, polar. So again, to get the net dipole moment, to evaluate the polarity of the molecule, we first need to start with the individual polarity of the bonds. So we said hydrogen partially positive, oxygen partially negative, hydrogen partially positive, oxygen partially negative. So now, like in I think physics does pretty good with kind of these directional vectors and kind of these, the length of the segment gives magnitude. If I were to line them up and all that, bottom line is I can find the center of positiveness. Center of positiveness, what are you talking about? Well, water molecule is a bent molecule, and we know it's bent because it has that oxygen atom has 2 lone pair electrons. So again, I'm kind of going back to our darn Lewis structures. The darn H2O molecule is oxygen, sigma hydrogen, lone pair electron. That oxygen atom is sp3 orbital hybridized. So its geometry, its electron pair geometry is tetrahedral. Okay. And that's why these bend this down. So, this is what we're dealing with. So, to me, you need to know the Lewis structure in order to understand whether the molecule is going to be polar or not. So, here we go. Center of partial positiveness. Well, spatially, it has partial positive, partial positive. The center of partial positiveness, right there. Okay? Partial negative, there's only one atom. So, the center of partial negative would be on the oxygen atom. So as I'm drawing it there, I would draw a plus, and actually I see diagrams like this. I would draw a plus here, and I would draw it up this way. As kind of the resultant vector, or that's kind of the sum of these two. Okay. So it's a spatial thing. So what I try to describe is shown right here. This actually, I know it's not kind of superimposed here, but think of this positive as kind of coming between 2 hydrogens. That negative would be from the electronegativity of the oxygen. So this right here, that is the vector showing the net dipole moment. So it does have a net dipole moment.
So don't need the arrows on both sides then?
Right, yeah, these are individual bond polarities, and this one is the net dipole moment. Yeah. And for like this one, if I was to find the center of positiveness, it's on the carbon atom. The center of negativeness, well, spatially we get equidistant from my 2 oxygen atoms, so that's also on the carbon. I have a slide coming up that says where your positiveness and your negativeness, if they are the same spot, there's no net dipole moment. If they coincide, they annihilate.
So that's when the dipole moment is equal.
Yes. Okay. Yeah.
So it is showing that.
Yes. Yeah, exactly, Allison. So yeah, this one doesn't have one of these to show because it's 0. Yeah. And then this is actually showing the mu, the net dipole. Yeah. You got it.
I've got a question about like why do we study polarity? Is it just like a way for us to understand the behavior of like molecules?
Yes.
And like what is that like transfer to?
A lot of things. So, for instance, that's a good question. A good one. Oh my gosh, oil and water don't mix because they're polarity.
So it's like.
And like the boiling point temperatures, like something that's not polar is gonna be weaker kind of connected to each other in general. So that will give it a lower boiling point temperature, more molecules. So it has all sorts of physical ramifications. Polarity does. Whether they mix and how volatile they are, those are big ones. The boiling point temperature. Yeah, I know, right? So let's look at methane. So this would be like methane CH4, where I have carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. And then these little 4 things are the individual polarities of the bonds. Okay. So, but hey, so if carbon is partially negative, that's pretty sure it's carbon activity, and hydrogen partially positive, does it make sense that the center of my positives and negatives coincide? So, dang, this would have a 0 net dipole moment. But what if I substitute out one of the, oh, I know. What if, check this out, what if I go ahead and now turn these all to chlorines and make it, I think it's chloroform? C instead of H4, CCl4. Same diff. CCl4 would also be non-polar. Yep. But now check this out. What if I change it up and you can see it looks like I'm going with three chlorines and one hydrogen. So I'll change the color I want to use. Okay. That could be my hydrogen. And then I have chlorine, chlorine, chlorine. Now, we kind of have an interesting tug of war because with regard to electronegativity, you can see that carbon must be more electronegative than hydrogen, but carbon is less electronegative than chlorine. Like, you know, I won't do any problems in here where you have to spatially identify where that would be because it's a little confounded. But what we say, this is partially positive relative to the chlorines and partially negative relative to the hydrogens. So I think, do I have a net? Oh, I don't show it. I'm thinking, well, to me, if I was going to draw on the slide, I'd probably draw the plus up here and kind of the negative down here, kind of between the legs. I thought it would be partial positive, partial negative.
So you like put both points because it's real like different.
It's polar, and what I was just drawing would be the dipole moment. It's definitely that dipole moment because the centers of positiveness and negatives don't coincide.
Right. So like if you're like labeling it the whatever it's called, the lowercase delta, the partial, like you put partial positive and partial negative, or you just put partial positive.
I think this is your question. I would. So what I'm drawing is I would go this. Oops. Kind of this. And this would be, like maybe this would saying partially positive up here. My pen's not being dumb. And then partial negative. Oops, sorry. Down here. Is that what you mean?
Go in with like the chlorines for partial.
Well, it depends on what you're after. If I am doing the, or I think we're talking about two different things. If I'm doing the individual bond polarities, I would get a little confused. I would do partial negative, partial negative, partial negative on the chlorine legs. Clearly partially positive on the hydrogen leg. And then it's confounded because the carbon is, And that's where I guess the difference here is you don't mix them. You put on blinders and you go bond to bond to bond to bond. You go blinders. And when we did that, we kind of have this evaluation where the carbon would be partially positive with regard to its connection to chlorines, and partially negative with regard to its connection. So it actually had, if I was drawing the individual ones.
Oh, yeah.
So what would be the vector that shows
the net dipole moment or the net dipole moment? I kind of, it was the one that's kind of, it didn't show up very good. I would show the partially positive here a little bit above the central atom, and the partial region, partial negative is kind of under here in the middle.
So,
and plus and then down here. Yeah. So that would be its net dipole. Yeah. Good questions. So just make sure we're on the same page. This is non-polar, non-polar, polar. So you asked kind of what the consequences of a polarity. One of them is this. I don't know where you would use this. I'm sure there's a reason. But if you have a molecule that has a region of partial negativeness and partial positiveness, like shown here, then if you have a pair of plates and you turn on the electrical field, can you see where this partial positive, this negative plate has all the partial positive ends lining up? This positive plate has all the partial negative ends of the molecules lined up. Isn't that kind of fun? They line up. And I kind of tease, but I'm not real familiar with the gel electrophoresis, but I think it kind of uses some of this. I'm not sure. It's been a while. Okay. So let's see what we got. With two atoms, like if your molecule is just two atoms, it's probably going to be polar if your bond's polar. Does that make sense? Just two atoms. It's got to be polar. Yeah. This is water. It's polar. We kind of saw before. We'd have the kind of the vector start down here and go up here, so it'd be partially positive, I guess it'd be the net dipole moment partially. The positiveness would begin here, net dipole moment, and the negative would be there. This is ammonia, and remember the deal with ammonia is it has a lone pair of electrons extending from the central nitrogen atom and then 3 hydrogens. So it looks like this. And this is where, I kind of apologize, Chem 1 and Chem 2 have to kind of intersect this way. But we talked about the structure or the geometry around the atoms, and we had to include lone pair electrons. See that is how many tetrahedral, exactly. But, and I think I avoided this in Chem 1, but Chem 2, then with regard to the shape of this simple molecule, you ignore, you ignore the lone pair electrons, and actually the shape is pyramidal. So it's a pyramid. And pyramids, oh? Okay. All I was going to say is pyramids, or put this over my head, not pyramid over my head, but. So pyramids are great for, in this case, we're going to have a partial, let's see, these are partially positive. So center of positiveness is here, center of negativeness is here. So our vector, our net dipole is going to be here. So,
sorry, no, she's breaking down the question.
Okay, so in biology, in whatever science classes, they talk about like liquids and polar heads.
mm-hmm.
So would the polar heads be the negative?
Mm-hmm. Yeah, they're usually hydroxyl groups with an oxygen and probably an oxygen, but a hot little oxygen head that's partially negative.
Partially negative.
Mm-hmm.
That's what I was thinking. You said the oil and water mixing.
Mm-hmm. Yeah, you can get it to mix if you turn it from oil into something else. Give it a friendly end.
So the net dipole moment is like the overall.
Yes.
Right. Okay.
Yeah.
I just want to make sure that's not.
Yep. Good question. Okay, so these are all polar. Net dipole moment. So the net dipole moment is basically adding just the bond polarities together. Now I'm going to give you some blah blah. So literally what you do, now this isn't, literally what you do is you take the two charges, you multiply them together, that's what, so your magnitude, the product of the two charges. Multiply them together and then you multiply by their distances. So the unit of these dipole moments, net dipole moments we've been talking about, the fundamental unit of charge is a coulomb, and then you add in distance there, so it's coulomb meter, which gives you a debye. So the debye is actually the unit for your net dipole moments, your individual polarities. Coulomb meters. Okay, now this is not blah blah. So, kind of some generalities. I said if you find the center of opposite, you find the center of positiveness, and if they lie in the same region, the same place, then they annihilate each other. So the whole molecule is neutral, nonpolar. The net dipole moment is 0 if they coincide. If they don't coincide, then, well, I guess if you found the center of region of positiveness and you found the center of negativeness and they don't coincide, then you're just a hop, jump, and a skip away from going ahead and just kind of drawing in the vector we've been talking about. Where the positiveness is, that's going to be the start of your net dipole moment. Where the center of negativeness is going to be the end of your net dipole. So, okay, carbon dioxide. It's nonpolar. It's kind of the tug of war. The region of negativeness and positiveness coincide. There's the full Lewis structure. And this is kind of showing you the tug of war. These would be the individual polarity of the individual bonds, chemical bonds. And the net dipole moment is 0. Now, this tug of war is different. So that was CO2 or carbon, 2 oxygens. This is kind of what I said before, carbon with an oxygen, carbon with a sulfur atom. Now, I don't have the Pauling values right in front of me, but which one does it appear has is more electronegative, oxygen or sulfur? Oxygen. And that's consistent with, what we know about the periodic table. We said electronegativity increases. And so then it's kind of like tug of war. It's like, oh, dang, it's more negative over here. Okay. So, again, what do you guys think? Center of negativeness. Wow. So center of negativeness would be swung over here, don't you think? Kind of off center to the left of the carbon atom. Yep. And we could make the center of positiveness maybe, I guess it'd be on the carbon atom. So, that's probably what I would do. It's kind of lopsided. So, what do you think? Polar or nonpolar? Polar, yep, because this would be its net dipole moment. Kind of like that-ish. Something like that.
Well, wait a minute. Okay, so carbon. Oh, it's equal to sulfur.
No, carbon. Oh, carbon and sulfur are, their electronegativity different, but they're not as different as carbon and oxygen. So yeah, sulfur. Oh wow, they're the same on this scale. So what you're saying is there really shouldn't be any. Using a different scale. Did you hear what she said? Okay. Stop. Very good. Water, we've talked about water. Those vectors shown are the individual bonds polarities. And this is showing you, if you add those two bond polarities together, you get this one, where this is the center of positiveness, center of negativeness. And the D stands for units of
It's like D-Y.
divide. Kilometers, yes. Units of divide. Very good. And I don't think you can have negative net dipole moments. I think it's 0 or positive. I think we looked at these the other day. This is like a hot potentiometric sort of map where this is the partial negativeness and this is partial positiveness, kind of showing you the kind of the individual electron cloud. So in general, which generalities are good, molecules that are symmetrical, if they're symmetrical, then their centers coincide. And if their centers coincide, it's nonpolar in general. In general, if it's the shape is lopsided, like this shape is lopsided, it's not, does it have any degree of symmetry? I don't know. But this would be a non-symmetrical shape. This is NH3. And it is polar. So what shapes are, now these would be molecular shapes, not electron pair count. These are the shape of the molecule. What works well for a molecule? Well, the tetrahedral, that was this one we did, or the CH4CCl4. Sorry guys. Tetrahedral, trigonal planar, I brought one of those too. This one works well. The centers annihilate each other as long as these are the same elements. Okay, if you swap one out, not so much. If they're the same element, or if they have the same Pauling electronegativity, then the centers coincide and it's nonpolar. And then this one, it depends. Linear, it depends. If I go ahead and take this one off and make sure they're equal, then we're back to it being symmetrical, coincide. This would be like CO2. The centers of positive negatives coincide and it's nonpolar. Non-symmetrical would be like water. Okay, this one. Pyramidal. So remember I told you a minute ago that ammonia is pyramidal. Okay, the shape of the molecule is pyramidal. And then this one, if it's linear, but if you swap out one, you're like, dude, that's not symmetrical. Okay. So I've got some units of net dipole moments for some molecules here. So for instance, if we pick on H2, okay, where you have hydrogen bonded to a hydrogen, look, its net dipole moment is 0. That makes sense because it's nonpolar because they're the same electronegativity. Yeah. HI has a degree of polarity, and these are increasing polarity. So with increasing net dipole moment, increasing net dipole moment just simply means that I have more of an electron. My electronegativity difference is greater. These are all bent. Okay, well, actually this one's linear. The first 3 are bent. Notice that the first 3 have a net dipole moment, and the last one, CO2, is linear and has no net dipole moment. Okay, so over here, oh, I see, we're doing pattern. This would be a central atom with 3 atoms scooting from it. Examples listed here. The BF3 is this one. If you draw a loose structure, which you might need to, BF3. Remember boron? What's weird about boron in these structures? 6, yeah. I only want 6, yeah. So when it bonds with 3 fluorines and you do a little structure, you're going to see that this is what it looks like. We have a bunch of lone pair electrons on there, 3 fluorine atoms. But this is sp2 orbital hybridized. Okay, so that would be nonpolar. Otherwise, it's polar. Okay, so just so we're all on the same page, if your net dipole moment is 0, what does that mean with regard to polarity? Your net dipole moment is 0. Is it polar or nonpolar? Nonpolar, very good. So those are all nonpolar. And they're nonpolar for a reason. If you look at their little structure, their centers and positives and negatives coincide. So they would all dissolve in each other. Okay. I feel like some of this, for this particular unit of material, I feel like I just rehash it. I'm like, really? We already talked about that. So CCl4, tug of war, centers of positives and negatives coincide. You tell me nonpolar. CHCl3, now we're substituting, we don't have equal little things connected to the carbon, so the bet's off, it's not symmetrical anymore, and we definitely have a net dipole moment, it's polar. So with these compounds, which one is nonpolar? Methane is nonpolar. Why? Because it's symmetrical. Yep. So we have nonpolar, polar, polar.
I guess the water's constant too,
Yeah.
but it's spatially it's correct.
It is, yeah, there's a line of symmetry, but not a point of symmetry, I want to say. It's a different type of symmetry. Yeah. Yep, you're right, it's definitely got a degree of symmetry. So we would call this tetrahedral, the shape of the molecule, we would call this pyramidal, shape of the molecule, bent. See, it just feels like I just keep repeating myself. CO2, nonpolar. BF3, I know this doesn't look like the right, but this one's better. Actually, the center of negatives and positives coincide, nonpolar. CH4, nonpolar. Now this has got to be polar, doesn't it? Yep, that one's polar, and this one's polar. Okay. So in all this talk about, this was a Chem 1 term, Gen Chem 1, where we talked about, we counted from the final of the structure, we pointed our finger at an atom and counted lone pair electrons, remember this? And counted sigma bonds. And if it was 2, it was sp. If it was 3, it was sp2. If it was 4 things, it was sp3. And we got the geometry around linear, trigonal, planar, and tetrahedral, respectively. Don't confuse that with the shape of the molecule. Just a few minutes. There is a class after this, but we got the room for a little while longer. Okay. And, you know, I'm making a big hairy deal out of this, and actually it is a big hairy deal. But when we go to talking about polarity of a molecule later on, where the shapes aren't so simple, like 3 or 4 atoms, then the polarity changes up a little bit when we assess polarity. Okay, so make sure you keep the shape of the molecule separate from the shape of the hybridization, shape associated with the hybridization around an atom. Oh my gosh. Doesn't it seem like there's 10 billion? Every once in a while, I'll tell myself, every once in a while, I'm going to go back and listen to my lectures. Like I'll call something polar was non-polar. Like, oh, I get my lefts and rights mixed up too, so that all works. Okay. And as you're doing problems, remember that I've got my answer keys posted. So if you're like, I get all of them except for this one, well, go take a look at the answer. So don't confuse the polarity of the molecule, which we identify with the net dipole moment, with the polarity of the bond. So now I bet you are convinced that it's possible that a molecule can have polar bonds, but the molecule itself can be nonpolar. Dun, dun, dun. Part 1. So tomorrow lab, and there's a pre-lab, and if the roads are bad and you don't want to try them, you know, give me a text or whatever. And if the roads are bad and I don't want to try them, I will send you an email.
Yeah, because I heard it was supposed to be like freezing rain tonight or something.
Yeah.
It's
And
supposed to go.
9 tonight. 9 tonight, tomorrow morning.
I do live in the country, so the roads up there.
Yeah. Don't risk your life. We'll figure something out. Yeah. You only what?
It's a chemistry.
I only missed the coolest lab ever. No, I'm just kidding. I'm just kidding. I think this lab, you'll read in you'll have to look it over for your pre-lab. But I don't think you'll be using the lab bus, but I don't think you need a stick for it. But you can use the same lab notebook. Don't forget to bring your lab notebooks and a pen. And we'll relinquish the room. My friend.
Have a nice day.
Thanks, you too.
Bye-bye.
Bye-bye.